Recording. Okay. Alrighty. So we are in slide number 6. So we left at a valence cell electron pair repulsion theory and structure of molecules in last class. Uh, so what this theory says is that let's say draw a molecule like the carbon is here. So if we have a molecule like this CH4, let's say the C is connected with four hydrogen, one hydrogen here, one hydrogen here, one hydrogen here, one hydrogen here. So if you draw this molecule here, it looks like this one. See, like this one, right? You see, if you draw like this looks like this one, just like this. So this is the carbon here. This is this bond is this bond. H is there. This H is there. This is this bond, and this is this bond. It looks like this, right? But according to valence bond electron, valence shell electron pair repulsion theory, this molecule doesn't look like this. Although we draw like this in paper or in the board, it doesn't look like this. So if you look the angle here, so the angle between this one and this one here is 90. This one and this one is 90. This one and this one is 90. This one and this one is 90. So if there were no repulsion between this electron and this electron, this electron and this electron, this electron and this, or if there were no repulsion between this electron here, the molecule would exactly look like this. Make sense? It's just like the planar molecule, how we draw in paper, right? But what happens is that, so it looks like 90 degree here, 90 degree here, 90 degree here, 90 degree here. But these molecules are not like this. So this is not the structure. What happens is that this, the electron pair here, this bond repel this one, this repel this one, this repel this one, this repel this one. So they are repelling each other, right? So what happens is the molecule takes the shape like this, like this. So it's not, you see that? So if you put like this, so these two things are coming toward you, and these two are going away from the board, right? Make sense? So these two. So if I hold like this, they come to hug me, and they are going away from the board. So actually the molecule look like this. Why? Because this electron is repelling this one. All these 2, 4, 6, 8 electrons are repelling each other. So they try to take a position in such a way that there is a least amount of the repulsion. Make sense? So this is the most stable structure. This is not a stable structure. So if you look the bond angle between this one and this one, 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 the bond angle would be like this. So this is a C here, and then this, let's say, draw the structure. So this one is like this. So like this one, and one is coming toward me like this, and then one is going away like this. So one H is here, one H is here, one H is here, one H is here. So it looks like that, and this, the angle between this and this is not 90, this is 109.8. And the angle between this and this is not 90, this is 109.8 degree. And then the angle between this is also 109.8, 109.8. So the molecule are most stable if the angle between the atoms is 109.8 degree. Make sense? So those, like these small angles are not possible. So why it happens? Because these electrons are repelling each other, and they try to be as far as possible by repulsion. So the least repulsion, or the most stable structure is that when these atoms are 109.8 degree apart. Make sense? So if you see this structure here, so how I wrote is like this. So if I put like, you put like this, this is this atom, this is this atom, and this one is going away, this one, and this is coming toward me. So this one, you see that this is called Weiss formula. So this one, if you look here, if you see something like this, so this is like this. So I'm holding this molecule like this, and this one is this one, this one. Now this one is this one, and this one is coming toward me, and this one is going away from this board, like pointing in. So that's how we make sense. Good. So this is the structure. So I buy in $20 from Amazon. So if you if you plan to take chemistry in future for your career, maybe you want to buy one for $20 and play in home. So it gives more understanding of the chemistry. Yeah, good. So like this one. So this is called the valence shell electron pair theory. So why the CS4 is not like this and like this? Because there are 4 electron pairs. So one pair here, one pair here, one pair here, one pair here. So those electron pairs are repelling each other with a great force in such a way that they try to stay as far apart from one another. Make sense? Just like the social distancing. Yeah, they are repelling each other. Good. So this is very important. So if there was no this repulsion, the molecule would just look like flat like this. Flat. Yeah, this is a flat molecule. So this one. So if you look the repulsion this theory. So let's talk one example here. This is oxygen and this is hydrogen and this is hydrogen. So hydrogen has 6 electrons in outermost orbit. So 2 are here, 4 here. So they give 1 here and 1 here. So they have 6 there and hydrogen has 1. So if you count the electron around hydrogen, there are 2 here. Around this hydrogen, there are 2 here. Around this oxygen, 2, 4, 6, 8 here, right? Like that. So what happens is that according to this theory, so these are called lone pair. You see here. So this guy and this guy, one lone pair. This guy and this guy, another lone pair. So there are 2 lone pair and 2 bone pair here. So these are called lone pair. These are called bone pair. So this one repel this one, and this one repel this one. So what I'm saying is there are 2 electrons here in this region. There are 2 electrons in this region. So these 2 are repelling this one. These 2 are repelling this one, right? So they are repelling each other. And this one is repelling this one, and this one is repelling this one. This one also repelling this one. So this, and also this bone pair and bone pair are repelling each other too. So if all electrons are repelling each other, make sense? So what is the maximum repulsion force here? So the repulsion force, this lone pair and this lone pair repel each other with a great force. Yeah. So let's say lone pair and lone pair repel with, let's say, 5 Newton force, 5 unit force. So like the 5 unit force, I'm just giving that 5 unit force. So this guy and these guys are repelling each other with 5 unit force. Now this one, this is a lone pair and this is a bone pair. So lone and bone pair are also repelling each other. Well, lone pair and bone pair. So this is lone pair, this is bone pair. They are also repelling with each other. So that force is not that high. So maybe that is a 4 unit force. Yeah, a little bit smaller. So these one and this one are repelling with a great force. These one and this one are repelling with small amount of force, like 4 units. And then now this one and this one is also repelling. So this is bone pair, this is bone pair. So this is bone pair, this is bone pair. So maybe they are also repelling each other, but with very small amount of force. So something like this. Make sense? So because of this thing, what happens is that this and this are repelling each other. So they are repel this bone down, this bone they repel down. So the structure of water molecules look like this. Like this. Make sense? So if the repulsion was equal, so if the lone pair also 2 unit, the lone pair bone pair also 2 unit, bone pair also 2 unit force, what would happen is that they would repel each other and then they would assume 109.8 degrees. Make sense? Like that. So good. So what is the structure of the water molecule? It's a bent like a V shape, like a V shape. So I show you here. I have a lot of yesterday. I make a lot of these molecules. I'll show you. Let's put it here, and the water molecules look like this. Yeah. So this is red is oxygen here. This is hydrogen here, and this is hydrogen here. And they are not showing this 2 lone pair here. So it's only they are showing the molecule here. Make sense? So water molecules looks like this. So if I put it here, it just exactly look like it. So oxygen is at center. So they are not showing the 2 lone pair and 2 lone pair here. This is hydrogen here, this is another hydrogen here, so this is a bond, this is a bond. So this is a water molecule. So in exam, I will put you some molecules, and I ask you, what is the structure of this molecule? Is it like bent like a V, or it's like a linear? So we will look those, yeah? Good, so this is a water molecule. Now, so why, if you look, measure the bond angle of the water molecule like HOH, it's about 104 degree. It's not 109, it's about 104 degree. Make sense? So why it is 104? Because this electron and this electron are pushing this bond and this bond down, so it is 104. If they didn't push, what would happen? It will be 109.5, because there will be 4 pair of electrons there, and they would orientate in such a way in 4 directions, so that the angle between them would be 109.8. Make sense? Good. So like this one. So this is a slide 6. Now let's look another one. Slide number 7. So in slide number 7, there is two things we need to look. One is the electron pair geometry, another is a molecular geometry. So the electron pair geometry is not that important. Molecular geometry is important in chemistry. Yeah? So let's look one thing here. So this is the oxygen here. So oxygen, I'm in the slide number 7, NOF2. So if you look there, there is a 4 electrons around oxygen like that, and here is a fluorine, here is another fluorine, here is another fluorine. So this is, if you look here, what is the electron geometry? So these are 2 electron are, this bond is 2 electron, this bond is 2 electron, these 2 electron, there are 2 electron, and there are 2 electron like this, right? So if you look like in the structure, it exactly look like this, like this. So this is a oxygen. So in the middle, this is a oxygen. So this is 1 pair of electrons. So I take this 2 out here, and it looks like this, like this. So this is fluorine, this is fluorine, this is oxygen here, and maybe I put like this way, right? So this is fluorine, and this is 1 electron pair, this is another electron pair. Make sense? So there is a space, but there is no atom here. There is space. There are 2 electrons here. There are 2 electrons here, but there is no atom here. Make sense? So how, if you look the molecular geometry, how does it look like? The electron pair geometry, how does it look like? This is 1 pair, this is another pair, this is another pair, this is another pair here, right? So it exactly look like the tetrahedron, like a CH4. Make sense? So this is called the electron pair geometry. Electron pair geometry. So electron pair geometry is 1 pair here, 1 pair here. So this is this one, and this is this one, and this is this one, and this is this one. Yeah. So electron pair geometry is a tetrahedron. Make sense? There is no atom here, there is no atom here, but there are 2 electrons, there are 2 electrons, but there are atoms here. Make sense? Good. So electron pair geometry. But to look the molecular geometry, so this, if you look the electron pair geometry, this is tetrahedron, 4-way, just like the carbon, right? Tetrahedron like this, right? Tetrahedral structure. But if you remove these 2 1, how does it look like? That's the electron pair geometry I just finished. Now let's look the molecular geometry. So this is a molecule. Now I take this one and this one. How does it look like now? This is a molecular geometry. It looks like a V shape, right? The bent V. So this is a molecular geometry is V shape, or you can say the bend. So this is oxygen here, this is fluorine, this is fluorine. Make sense? So that's the difference between the molecular geometry and electron pair geometry. So electron pair geometry is not that important, molecular geometry is important. So I might put in exam, so I give you the structure like this. So I say, so oxygen is like this, and one is fluorine here, another fluorine here. What is this? What is this structure? What is its molecular structure? I asked that, right? Now you just look at, are there lone pair? Yes, this is a lone pair, this is a lone pair. Then if there are lone pair, they are repelling each other. So this bone is pushed down, this bone is also pushed down, and what happens is it looks like this. The bend shape. Make sense? So if you don't see the lone pair here, So if there were no dot here, it would exactly look like the linear, like the straight line, like this one. So if there were no lone pair, I think yeah, it would look like this one. So suppose there is no dot here, there is no dot here, no dot here, no dot here. So then the molecule would look like this, linear. Make sense? 180 degrees. So if you measure the angle between this one and this one, 180, 180. Yeah, good. So this angle would be a straight line. The angle would be 180 degrees. But if there are electron pair here, they immediately start to push this down, and this goes down, and the angle, the structure look like this. Make sense? That's very important. So if there are electron pair in the central atom, it just immediately start to bend. Yeah. But if there is no electron in the center atom like this, this does not go down. So it just stay like that in the one line. Make sense? Linear. Good. So like this. Now that's OF2. So I already write there. Electron pair geometry is tetrahedral because there are 4 pair of electrons. They are orienting in 4 directions. So that's a tetrahedral, and molecular geometry is bent. Now let's look the water. How about the molecular geometry and electron geometry of water? Again, water is this one O, this is H, this is another H. So one pair. How many? 1, 2, 3, 4 pair, right? So the 4 pair of electron always point in 109 degree, 109.5 degree. Tetrahedral geometry they call. Yeah. What I told you at the beginning. This is a electron pair geometry. So this one and this one are going away, and this one are coming toward us. So this is the electron pair geometry is tetrahedral. We call tetrahedral. Tetra mean four side. They are directing 4 side as in CS4, and the angle between it should be angle between those electrons should be 109.5. So if you measure this one, 109.5, 109.5, 109.5, 109.5, something like that. So this should be like that, but they don't behave like that. Why? Because of the electron repulsion theory. So this repel this one, this repel this one, this repel this one, this repel this one, this repel this one. When they start to repel each other, and these two repel with a great force, then this one and this one repel with a little bit small force, and this one and this one repel with a small amount of force. So the molecular geometry would look like bent like this. Make sense? So you can see that. So these two electrons like this. So the molecular geometry is bent. This is molecular geometry. Make sense? Good. Now, how about the let's say so I have the CO2. There is a CO2. So I'm going to show you the CO2. So CO2 looks like this. So this is if you look the structures of CO2 looks like this. C double bond O here, double bond O. This is called the carbon dioxide gas. Yeah. So you see here it looks like this one. So this center is the C, right? This black is C, and this 2 line represents these the 4 electron, 2 bond here, and this 2 line represents this electron here. So this is linear, it is straight line. Make sense? Like, so if they were electron here, the dot here, they will bend like this, and the structure would look like a C double bond like this. But since there are no lone pair there, so this looks like this. Make sense? So if you see any dot at the central atom, immediately start to bend down. Yeah. So what is the structure of the carbon dioxide? It's a linear. Yeah, good. So that's that one. And let's look at BBr3. So BBr3, all right? So like this one. So I'm going to look this one now, 3. BBr3. So here is this central atom is boron, and this is Br, this is Br, this is Br, right? So BBr3. So let's say here I have B here, and one Br is coming like this, another Br going like this, another BR is going like this. So if this is the center, around that center is 360 degrees. So then if you divide equally, this is 120 degree. This is 120 degree. This is 120 degree angle. Yeah. So the angle between this one and this one is 120 degree. The angle between this one and this one is 120 degree. The angle between this one and this one is 100 degree. So it's a plane. So if you put in a hand, it just stands like a plane, right? It's a plane. Make sense? So this is called a trigonal molecule. It's called trigonal because it looks like a triangle, right? So if you connect this one, this one, this one, this one, and this one together, it looks like a perfect triangle, right? So it's called a trigonal molecule. Yeah? What happens if you have something like this? So since there are no dots there in the center, it looks like a very planar molecule, right? But what happens if you have some dot here? So the free electron there, like the lone pair. So if the lone pair were there, what would happen is that there is a lone pair here, and there these lone pairs start to push this bond down, and this bond down, and this bond down, and it would look like this. It would look like BR, and the BR. So they all be pushed down. Yeah. If there were a lone pair here, this was pushed down like this. This was pushed down like this. This was pushed down like this. Yeah. And it would be pyramidal, like the pyramid. Yeah. But since there are no dot here, so the all these three bromine and the boron sit in a plane, one plane. Make sense? Good. So if you see the lone pair at the center, you immediately should start to bend the molecule like this. But if there are no lone pair, it should look like this, Yeah, in the same plane. You see that? This is the board, this is the plane of the board, and this is a boron. This is a boron here, and this BR is here, this BR is here, this BR is here, and like this. Yeah? But if there were a lone pair here, it would look like this. So this bend down, and you cannot put in that plane. It would look like this. Yeah? Good. Now, another one here I will show you for the, so BBr3, so BCl3, so they all are trigonal planar. Now let's look at the ammonia. So this is a very famous molecule, ammonia, right? So ammonia is a very famous molecule. So ammonia look like this. So if you draw the ammonia, so put nitrogen here, and nitrogen has one pair here. So nitrogen has hydrogen, hydrogen, hydrogen. So nitrogen has a structure like this. So outside of the nitrogen there are 5 electrons. So 1, 2, 3, 4, 5, and one electron coming from hydrogen, one electron coming from this hydrogen, here one coming from hydrogen. So ammonia molecule look like this. So there are 2 free electrons in the valence shell, so lone pair. Make sense? So once you have this lone pair, so this is not like this. So if you have a lone pair, it doesn't look like this. So if that was not, if these 2 electrons were not there, it would look like this. So this hydrogen would take shape here, and it would look like this. Make sense? But that was the case of the boron. But in case of the ammonia, what happens is we have 2 electrons here. They are called lone pair. So they push this one with great force. They also push this one with a great force. And they are also pushing this one. So when they are pushing that way, it looks like this one, pyramid. You see, it looks like a pyramid, right? Like a pyramid. So if we put like this one, so it's not in one plane like this. So if you put here, so this all 3 are coming toward you. Make sense? So this is also the bent structure. So this looks like this one. So nitrogen here, hydrogen. This hydrogen is pushed down. This hydrogen is already here, and this hydrogen is also pushed down like this, and it looks like this. It's a pyramid. Make sense? So the question sometimes is why BF3 is a trigonal planar? Because there are 3 bonded atoms and there are no lone pairs, so they all are in the same plane. So that's a trigonal planar. But what in case of the ammonia? But nitrogen has 2 electrons here, and these 2 lone pair electrons are pushing those bond pair with a great force, and they bend the molecule shape, and it becomes like a pyramid, like this. Yeah? Different? So this one is this one, this one is this one, this one is this one. So it looks like pyramid. Tripod, right? Tripod like this. You can put like this. Ammonia is like that. Boron is like this. You see, that's a planar, but this is a pyramid. Okay? It's very important. So then if you measure the angle here, maybe the angle between this hydrogen and hydrogen was about 107 degree here. So this angle is about 107 degree, not 109 degree. So the ideal angle would be 109.8 if there are 4 pair of electrons. But if there are a lone pair, the angle cannot be 109.8. It reduces to 104, 107, 102, something like that. Yeah, good. Now, what do we have here? So those are like that. So you can just practice yourself. So here are some bone angle. So I write some bone angle here in slide number 8. So CH4. How does the CH4 look like? I already showed you. CH4 look like this, right? Where is the CH4? So this is the CH4. So this is really important. So if you don't have this model, you will just keep struggling throughout your life. But if you have this model, you just immediately know what's going on here, right? So like this. So what is the bone angle? This is the CH4. What is the bone angle for this one? So I already told you. So C. So one H is here, another H is here. So another H is coming toward you, one H is coming toward you. So you may hold like this. So I put like this. So this one, this is a C. So if I can put this CH like this, so this H you can put like this. This is going away from the board like this. So you can just put the dot like that, and this is coming out from the board toward you. So you can put a ways like this. So CS4 looks like this, right? And then if you measure the bone angle, they are 109.8, 109.5 degree. There are no lone pair. Why? There are no lone pair here. There are no dot here. Yeah. So 109. Now, if you look the ammonia, what is the bone angle? I already showed you. So this is the ammonia. So this is the ammonia here. So the bone angle here was 109.5. In case of the ammonia, it's a 107.5. Why in 107.5? Because we have some lone pair here, one lone pair here. So they are pushing these 3 hydrogen down. Make sense? And then what else here? Water. I already told you about the water. And I have a water molecule here, like this one. So water molecule has even smaller value of the bone angle, 104.5. So why 104.5? So if you look for the nitrogen, there will only one lone pair, only lone pair. So the angle would make 107.5. But if you look the water molecule here, like this, water has 2 lone pair like this. So this is 104 degrees. So since there are 2 lone pair, the force of pushing down is great there, right? So the angle becomes very small. Yeah, they are just pushing with a great force there. But here there are only 1 lone pair, so the force they push with is not that high. So the angle is a little bigger here. There is it's smaller here. Make sense? So if there are more lone pair, they push with a great force, and the angle becomes smaller and smaller. Yeah. Make sense? So the ideal bone angle should be 109.5 in case of C or something connected to 4 ways. Yeah? Good. So here it is now. What do we have here? Now let's go to the slide number 9. So this is important for the lab number 13. There are a lot of molecules. You need to do this kind of thing. Yeah? In lab number 13. So now let's talk about some other thing here. So 2 pairs of electrons, meaning that let's say you have some central atom here. Let's say this central atom is A, like C or N or B, right? So this is like this one, and put another electron here, and another atom here. So it's like the AX2, like is like the if this one is beryllium and this one is fluorine, this one is fluorine. So they give the AX1, AX2, AX3, something like that. Yeah. So it's the same thing. So something like this. So if you have something like this and there are no 2 pairs of electrons, there is one. This is 1 pair, right? This is 1 pair electron. This is 1 pair electron, like this one and this one. So if you have something like this, AX2 type of thing, so this is 1 pair, this is 1 pair. So 2 pair electron. So this is 180 degree. Always 180 degree. Make sense? 180 degree. That's a AX2, and the example is BEF2. So they are trying to be as far as possible. The farthest distance they can be is 180 degrees. Make sense? Good. So let's take another one, AX3 type molecule. AX3. So AX3. So you have a central atom and there are 3 pair of electrons. So this is A, the central atom. Now there is 1 pair electron here. You have another pair electron here. You have another pair electron here. So it's just like this one. Where was the boron? Like this. Exactly like this. Make sense? So central is A, and this one X, and this one X. So how many electron pair we have? This is 1 electron pair, another electron pair, another electron pair, 3 electron pair here. So if this is the case, the angle between them is 120 degree, and it's just exactly like this one. Yeah, like the boron. BF3, BX3, BBr3, I don't know, whatever. Make sense? So now let's go to AX4 type. AX4 type. So what is AX4 type? This one, AX4 type. So in case of AX3, the bond angle is 120 degree and they are in one plane, like the BF3. Example of this one is BF3. Now let's talk about the AX4 type. AX4 type. So there is a central atom and there are 4 pair of electrons. So it's like a CS4. I already told you CS4. So you have A here and you have 1 bond here and you have 1 bond here and there is 1 bond going away from you and there is 1 bond coming toward you like this. Yeah, AX4 type. So you can put here X, 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 X. So this bond is I'm just holding like this one. So this is this X, this X, this is coming toward you, this one, and this is going away from you. It's trying to penetrate the board. This one is this one. So what is the bond angle here? 109.5. 109.5 or 109.8? I don't know. So this is a AX4, 109.5. 109.5. Yeah, like this. This is a CH4. So if the central atom that A is C, so other X, you can say CH4. So angle is 109.5, and we call this as a tetrahedral molecule. This is a tetrahedral. Make sense? Tetrahedral molecule. Now, so in my time, we didn't have the model like this, so I always struggle this all the way up to my master's and PhD. So I didn't know how this originates. Make sense? So like that. Now let's take about the AX5. So AX5. So I'm going to show you AX5. So now AX5 type of thing. So you have a central atom with the center here. That's A. And what happens is 3 are in the plane. 3 are in the one plane. I will show you what does it mean. Like in one plane, and one is going up like this, another is going down like this. So I will show you. This looks like this. So AX5 is like this one. So you see here, this one. So this one up top here is this one. It's going up, right? Like going toward the ceiling. Make sense? This one is going toward the ceiling like this, and this one is going down toward the ground, right? So like this. So this is going down toward the ground. This is going toward the ceiling, and then this one is in the plane, like in the equator. This is in the same plane with this one. So this one in the same plane. If you see here, these 3, 1, 2, 3, these are in the same plane. Make sense? And this one is going toward the ceiling. This one is going toward the ground. Make sense? So what we call is, so this is a triangle here. So this one is basically a triangle. So it's a triangle. So this is a triangle, right? This is a triangle. Make sense? These 3 are making this triangle. This one, and this one are triangle, making triangle. And this going up is called pyramid. And the going down is also called pyramid. So what we call is trigon. So the center here is a trigon, trigonal, and going up is giving a pyramid, going down is also giving a pyramid. So we call bipyramid. Make sense? Trigonal, bipyramid. Bipyramid. So if there is a central atom and there are 5 electron pair going from this the central atom, it looks like the trigonal bipyramid. Make sense? So they're in the center, in that equator. So if you think the central atom is the Earth, the 1, 2, 3 are in this equator, then one is going toward the sky, one is going toward the down. This is called trigonal bipyramid. This is very important for lab 13, yeah? So AX5 is trigonal bipyramid. The example is PF5. Now, let's look another AX6 type, and we are done. AX6 type. Now, let's see I forgot to tell you the bone angle. The bone angle would be like this. So the angle between this one and this one, and this one and this one would be 90. This one and this one would be 90. This one and this one would be 90. Maybe this the angle between this is 120 at the center, yeah, along the plane. Now, what else we have here is so it's already given. The angle between this planar, you can see here, this one is in this three are in plane like this. The angle between this one and this one is 120. The angle between this one and this one is 120. The angle between this one and this one is 120, right? But the angle between this one and this one is 90. Make sense? This one is 90. This one is 90, and this one is 90. Yeah. So like that. Good. So this is PF5. Now let's look at AX6 type of thing. AX6. So AX6, you have a central atom and like this one. So you have a central atom here, and 4 are in the plane. Previously, I have 3 in the plane. Now in this case, 4 are in the plane, and one is going toward the ceiling, one is going toward the ground, right? That's AX6. So this is called. And this is named a little bit different way. This is called octahedral. This is called octahedral. Octahedral. Previously, I told you when there were 3 here, when there were 3, 1, 2, 3 in the plane, in the equator, one going up, one going down. I told you this is a trigonal bipyramid, right? But if you have another X here, 1, 2, 3, 4, 5, 6 pair of electrons here, and this kind of is called the octahedral molecule. Yeah, and all the angles are 90 degree. All the angles here are 90 degree. So how is it possible all the angle 90 degree here? So I show you the structure here. So 1, 2, 3, 4, 5, 6, right? Like this one. So like this. You see here is like this. So this is A. So the central atom here is A here, and this one is going toward the ceiling. This one is going down toward the earth, and this one is this one. 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 So 4 are in the same plane, equator. Make sense? 4 are in the same in the equator. This is going up and this is going down. Make sense? So if you look the angle between this is this 90, this is this 90, angle between this one and this one is 90. So all angle between the electron pair is 90, 90, 90. So this is called octahedral. Yeah, this is SF6. So if you write the structure, that's a SF6. So if you want to write the structure, so central atom is S, one is going up like this one, and one is going down like this one, SF2. Now this one is this one, this guy is this one, and this guy is this guy, and this guy is this guy, like this. But although this and this one and this one doesn't look to be in the same plane, but in really, if you look the molecule, they are in the same plane. If you take this one, so this is the same plane, right? It's the same plane. Make sense? The 4 are in the same plane. Good. That's the SF6. Good. I think you learned something. Now, what else do we have here? That's a PF5, SF6. Now let's look some other structure. So I show you SF4 type of molecule here. So go to the slide number 10. Go to the slide number 10 and look the SF4. PF5 we already talked. So now let's talk about the SF4 kind of molecule. Yeah, SF4. So SF4 is what is SF4? So S 1, 2, 3, 4 like that, and there are no two fluorine atom, right? This is SF4. Yeah. So S F F F F, and there are 2 electrons here, and there are 2 electrons here. So it looks like this SF4. So how does it look like? If you look this structure, it looks like the seesaw. Probably you already played the seesaw when you were a kid, right? It's like this one. So this is S, this is S, and then this fluorine is going like this fluorine is going down like this, and this is one fluorine, this is another fluorine. Yeah, makes sense? Although I didn't have a same color material here, so I put the green here. So this is F, this is F, this is F, and I'm not showing the two electron domain here. So let's put the electron domain. So like this. So like this. So you see here. So this is the electron domain here. This is electron domain here. So I don't have fluorine here, but I have some electron. I don't have fluorine here. I have electron here. Right? Make sense? So what is the molecule look like? I'm not concerned with this electron now. What does the electron molecule look like? Look like a seesaw. Yeah? So it's like a seesaw. So it's like this. You know seesaw, right? Seesaw is like how we the kids play the game like this. SF4. Yeah? Good. So this is the SF4, and there are these two electrons. So what these two electrons do is they slightly push this bond this way. So it's a slightly bend like this. So this is S. So this is F. This is F there, and so this bond here is slightly pushed this way. This bond is slightly pushed this way, not like the state here. So this is a little bit bent toward the same side. Yeah? Make sense? Good. So that's the SF4. Now, yeah, there are a lot of things, so you can just read that one. So I do ClF3. Now, ClF3. So there is ClF3. Let's look at ClF3. How does it look like? ClF3. So there is a Cl, and then we have ClF3. So ClF3, right? How many electrons at the 2, 4, 6, 8, right? So this is a ClF3. So in case of the ClF3, one fluorine is going up, another fluorine is going down. Now ClF2. I have now ClF2, right? Now I have one bond here, one bond here, one bond here, like this one. And this is F, and there are no F here. There is just only the electron domain here, only electron pair here. Make sense? So this is a ClF3, and it looks like a T shape. So this one is like a T shape, right? Looks like a T, right? Good. Or you could write the another way. So if you want to write another way, Cl here, and this F, you could put this F here and this F here. So again, it looks like a T shape. ClF3 looks like a T shape. And there are two electrons here, there are two electrons here. They slightly push this down, they slightly push this down. So a little bit it is bent. So ClF3 is a T shape. Make sense? Good. Now, how about the xenon fluoride? Xenon Fe2. So let's look at xenon fluoride. So xenon fluoride. So it's look like this. So at the center you have a xenon, and then one fluorine is going up, another fluorine is going up, and there are three pair here. One pair is three pair, right? Xenon fluoride. One pair, two pair, three pair. We have three pair electron at the equator. So it looks like this. So like this one. Is that one? 2, 4, 5. So like this one. I think xenon fluoride. I put the xenon fluoride here. It's okay. So it's like this one. So like this one. So xenon fluoride looks like this one. So this actually this bond should be coming here like this. It's just a little bit doesn't work that way. So this center is a xenon here. So this electron pair is here. This electron pair is here. This electron pair is here. So they are all in the plane. So this one, and this one in the plane. Same plane. You see that? Same plane in the equator. Three pair of electron. And this one is going toward the ceiling, and this one is going down toward the ceiling. Yeah. And the angle between this is 180 degrees. So this is a linear. So angle between these xenon FF angle is linear, 180 degrees. Make sense? Because in the center, all electrons are there, and there the push is balanced. So this is a linear. So SF6, I already told you. Now let's look the BRF5. I have two molecules. Now let's finish this one. Now BRF5. So BRF5. Do I have a BRF5? So BRF5 245. So basically, I don't know if 1 2 3 4 5. I should have 5. So basically, in case of the BRF5, it looks like I didn't make a model there. BRF5 looks like this. So BR here, one lone pair here, one lone pair here, one lone pair here, one lone pair here, and one lone F here. You see that? So lone pair, not lone pair, BRF5. So BRF here, F here, F here, F here. All are in the same plane. So these are the in the same plane, and one F is going like this, BRF5. So this is called. So it does the down here. This is a square. So this is a square, and this is a pyramid. So we call the square pyramid. Do I have a BRF5 here? So I would show you BRF5. Looks like I didn't make the BRF5. So 1 2 3. Yes, we have here. So 4 and 5 like this. Yeah, you see here, this is this 4. 1 2 3 4 are in the same plane, right? You see that these 4 are in the same plane. If I put in my hand this 4 BR and this central BR just sit in my hand, and this F goes up like this. Yeah, so this is called square pyramid. So this bottom is square, and this is a square pyramid. BRF5 is square pyramid. So now let's look one example here. In case of the xenon tetrafluoride, xenon F4 is look like this. So xenon F4 looks like this. So 2 electron is going up there, 2 electron is going down there, and xenon is here, xenon F4. So this is a square molecule. Make sense? It's like this. It's exactly like this. Yeah, the plane. Make sense? So 2 electron is going up, 2 electron are going down. So if you want to put that there, so you could put like this, like this. So there is this is electron. There is nothing in this one. This is also electron. This is going down, and this central is a xenon, and this fluorine are in the same plane. Make sense? So this is a xenon fluoride. So this is a molecular geometry is square plan. This is square, right? The center is square, right? Like this line is square here, and then you see all these 4 are in the plane, same plane, like this. Yeah. So this is called a square planar. So this is important for the lab 13 and important for the exam too. Yeah. So I think we are almost done. So we will talk a little bit in next class, and probably we will finish this chapter in the next class. Yeah. Good. All right, everyone. So I'm going to stop this now.